Okay, good morning, everyone. We already have more than 100 people here. I'll start sharing my screen slowly. Um, there were already questions about the slides. They will be made available. So don't worry about that. Just a second, let me see. Okay, welcome everyone. A wonderful good morning from Zurich. My name is Frank, and we'll be going over together with Luca on working with RISC-V. We have 4 parts, each about 1 hour. Today we do 2 hours, and tomorrow we do another 2 hours. So in this first part, first hour, we are going to make an introduction to RISC-V ISA. What is RISC-V all about? Basic properties of it. We will talk about an implementation of it that we developed and which is now being maintained by a low risk called IBEX. And then we are going to see how the RISC-V ISA can be extended. We have a processor that we developed, which is now being maintained by the Open Hardware Group. Later on, Luca is going to talk about more advanced RISC-V architectures. And tomorrow, we are going to talk about concepts of making more with the processors, how we can get more efficiency. And then in the last part, we are going to talk about pulp-based chips. So if you have questions, feel free to post them on the chat. There are question and answer sessions. We will have about 15 minutes after this first presentation to go over some of the questions. And Luca is also online. He may also provide some answers while I'm still explaining. So just a few words about myself. Just call me Frank. Nobody tries to pronounce my last name. I'm a senior scientist at ETH Zurich. That means that I am older. I'm working with Luca since the beginning of the PULP project. And I'm mostly involved in digital design, low power circuits, and recently also open source hardware. So this is me if you want to reach me, and we will see more about that card in a few minutes, actually tomorrow. So let's get started. What is RISC-V? It's an instruction set architecture. It is a project. It's actually a longer project, has longer history at University of California in Berkeley. And it started in 2010. Let me just turn on my laser pointer. I hope it is visible. So essentially at the top, you see you have software. At the bottom, you have hardware. And in between is the instruction set architecture. It's a contract between software and hardware. So software knows what to expect from the hardware. You can develop it without even having the hardware there. And when you're developing hardware, you know exactly what kind of instructions, what kind of memory mapping you will be interacting with. So the contract is divided into 2 pieces. There's a user mode and a privilege spec. And in addition to that, not inside the ISA, you also have an external debug description how to interact and debug the system. So this standard is governed by a foundation. And ETHZ is a founding member of this foundation. And this foundation is necessary for the continuity. So we are maintaining as part of the RISC-V Foundation the rules and the descriptions maintained in there. RISC-V is special in the way that it defines not only a 32-bit architecture, not only a 64-bit architecture, but an extensible architecture. Currently, 32 and 64-bit are ratified, and there is 128-bit descriptions. But it's just that, it's just a description. It's not an implementation. And although the instruction set architecture is free, the implementations of it can be both open and closed source. So our specialization at Zurich is efficient implementations of RISC-V cores. We're going to talk about what we mean in efficiency later today. I mean, if you want to be very strict, what RISC-V maintains is basically a series of PDF documents. This is the web page. I was there yesterday preparing these slides. So you see here's a specification. You can see it as a PDF or the latest version that's been worked on GitHub, unprivileged, privileged, and debug specification. And what does this ISA define? Well, they define the basic words, the alphabet of the processor that is executing your program. So what you do is you write your program in a higher level language, in this case C++, and the compiler is able to map them to individual instructions that is being defined by the ISA. So it describes what is LD, what is LW, what is SLLI, what are these parameters, etc., etc. The good news is once you have this ISA definition, and the compiler will know how to translate it, and this translation will run on any RISC-V implementation, regardless of who made it, as long as the people making the implementation follow the rules described in the document entirely. By the way, this is a screenshot from an online compiler explorer, highly recommended, from Matt Godbold. The good news is, since you have a contract, it is possible to develop an ecosystem, meaning that you can develop a number of tools that is necessary to work with the processor, and not only develop software for it, but to use it. So there are the compilers, GCC LLVM, the bean utils, the utilities that you need to have to start your operating system, different operating systems, runtimes, simulators, and tools for debugging. This software is maintained by various people. For example, bean utils and GCC are maintained by Sci5, a Berkeley startup. The Zephyr is, for example, maintained by Ant Micro and the like. And below you can have a URL to describe more of the updated status list. Now, the main idea between RISC-V was to keep it very simple and have it expandable. The idea comes also that there is a very wide range of applications. So you have your small IoT devices, which are very, very small processors, all the way to large computer, high performance computing systems where you need a lot of power. So to describe this thing, they said, okay, we have different extensions, different standards in it, and we need to define it. So they say, okay, we start with RV, then we add the word width, and then we add the name of extensions. So in the user specification, you have a number of extensions when you look here on the left, and the only mandatory one is actually the the integer instructions. We are going to talk about that. And there are also some privilege specification. This is what you need when you need to run an operating system on it, exceptions, interrupts, virtual addressing, privilege levels, etc., etc. So if you take the example here, RV32IMC means that it's a 32-bit RISC-V. It implements the integer, multiplication, and compressed extensions, which have been defined here. As you can see, some of them are already written frozen, and some of them are not yet frozen. There is also what we have here, the non-standard extensions. We are going to talk about that later on. This is not all. There are actually many different extensions that people are working on, and the work goes in task groups within the RISC-V Foundation. So you may have an idea, you are a member of the RISC-V Foundation and say, hey, I want to start a task group on vector operations or user level interrupts. You start your task group, you're deciding on it, and the idea is to have that these things are then ratified and accepted and stay as standard, as a frozen standard. There are also some dedicated task groups within RISC-V Foundation. These are necessary for the memory model, marketing, external debug specification, security, etc. We are also contributing, we are a member of the foundation in select extensions like bit manipulation and packed SIMD. So first, to just clarify what is so special about RISC-V, you know that it is free. It means that everybody can build, sell, and make RISC-V cores available. So this is important. You can also sell them. There is no limitation saying that, hey, what you make has to be free. This is important for people to be able to develop also businesses around it. So it's a modern design. There is no historical baggage. The RISC-V benefited from the mistakes made by others. You don't need to remain compatible to some decisions that you have made 20, 30 years ago. And what is really nice, if you read the PDF that I was talking about, major design decisions have been properly motivated and explained. I have just one example, not a specific one, but when you read the PDF, you have at the top, they are talking about the endianness here, and then there is a footnote or there is a separate section written in italics where they properly explain what was the reasoning behind it, why did we come to this decision, what are the pluses and minuses, and why are we going this way. This is actually very good also for people to understand and follow what was the thinking behind it. The other thing is there is reserved space for extensions, and it's very modular. The extensions, we will come to it later, is really what makes it very interesting and exciting from a research perspective. It's an open standard, so you can also help decide how it is developed. You have to be part of the RISC-V Foundation. You have to contribute to the task groups. Obviously, it is a process. It doesn't go like you just say something and it immediately is ratified. Some of these things go, I mean, they are longer discussions, but the good news is it's open for contribution, and you know, there is a very lively discussions on some of the standards. Vector, for example, is very active these days. So I get this question a lot, so I just wanted to clarify the freedom in RISC-V is actually in the implementation. Because if you think about it, what you see in the ISA document, which is here for the RISC-V on the left-hand side, you can also find for other processors, for example, ARM. Here, this is taken from their ISA description. You see exactly how add works, how it is encoded, what are the bit points, and etc. This is actually needed. All ISAs want to publish this because you want to have software tools to be developed so that they can generate code for that ISA. So from that point of view, there are not many differences. You can see the same description that you can see for RISC-V, also for ARM, Intel, and all other major architectures. But the ISAs are closed. Only specific vendors can implement it. So if you want to build a core, you want to sell a core that implements this ISA, you have to license it or buy it from the vendor. Now the open source, you can have open source software for the ISA. This is possible, but you cannot build the hardware. Well, you can build it for yourself. You're not giving it to anyone. That's also possible. You know, everybody can at home look at the ARM ISA document and write something, but you cannot share it. You cannot sell it. You cannot work with it. So this is the freedom in the RISC-V. Also, because we ended up making a lot of those processors, we get asked, are these processors better than any other one, X, Y, Z? So you have to realize the actual performance depends on the implementation. So RISC-V does not specify any implementation details. This is on purpose. They don't want to put themselves in a corner. They're describing how the architecture is. What you do in the microarchitecture, that's the implementation, is up to the designers. But it's a modern design. The ISA is modern. It should deliver comparable performance to all modern implementations. So if you implement it well, it should perform as good as other modern ISAs. In our experiments, we see no weaknesses when we compare to other comparable ISAs, but we have to also say it's not magically 2x better. So it's a modern processor that works just as well as the others. Now, if you go to high-end processor performance, there is certainly a part of it has to do with the ISA, but implementation details, the technology capabilities, memory hierarchy, and power management and other things are actually more important in that regard than the only limitations of the ISA. So while we are being fair, we should also say what is not so good about RISC-V. Well, there are a few things. It's still in development. Some standards, vector, privilege, are still being refined, and refined means that there are still some tiny changes happening and they are adjusted. The tools and development environment needs to catch up. It's also difficult to sometimes catch up when some things are still a little bit in change. There is no canonical implementation. There is not the RISC-V core. So it is free to implement. Many people did so, including us. And as a result, there are many RISC-V cores. There are probably 100 implementations available in the wild at the moment. And you can make an argument that higher end out of order superscalar 64 whatever cores are not yet as mature as what you can find in the industry. So you're not competing with Intel Xeons or higher end ARM processors. In theory, there's nothing to prevent a RISC-V based Linux laptop, for example, but it will take some time until the RISC-V implementations can compete with other commercial processors. To be fair, it also needed hundreds of months of work for those processors to come out. So it's not just that PDF was missing. So after having this brief introduction, so let's take a look at what is happening. So it's called reduced instruction set. And one of the fun parts of it was all the instruction set could be printed on one A4 page. And this is it. It's sometimes known as the green card, because in the Hennessy Patterson book, in the first and last page, this was printed on a green cardboard. Here you see everything. So it is divided in parts. So this is the only instructions that are necessary for RISC-V. There are about 30 or so basic instructions. That's the integer thing. So you have a load, shifts, arithmetic operations, logical operations, a few branches, jumps, and that's it. It is so basic that something that a lot of people would consider basic are not even included. Multiply, divide, and remainder functions are actually an extension that are added on top of this thing. So if you want to support hardware multiplication, you are adding an extension called M. Similarly, we will talk about them briefly, compressed instruction extensions, C, so that adds a few separate instructions. And then you have the things needed for privilege mode and atomic extensions, A. And then here at the bottom, you see floating point extensions, that is F. The rest of the sheet is actually describing different parts of the instruction format and the calling conventions, etc., etc. That's it. So this thing gives you the main instruction set all in one page. Now, just to give you some basic overview, there are 32 registers defined. Each is depending on the architecture you're using, 32, 64, or 128 bits long. They're named X0 to X31, and X0 is always hardwired to 0. So that register is always 0, you cannot write to it. Later on, they realized that for very small applications, maybe 32 registers is an overkill. So they are developing a standard E extension that is the same. The only thing that changes is it only uses 16 registers. So instead of RV32I, there's also an option of using RV32E. We will have a small processor that we call micro RISC-V that uses this. In addition to that, we have one program counter that tells you where to fetch the next instruction. We RISC-V use byte-based addressing, so the program counter increments by the word length. If you're using floating points, there are 32 additional floating point registers with the same length. And for more, there are things that are needed when you are running an operating system. They are not part of the internal registers. They are called control status registers. And there's an encoding for up to 4,096 registers reserved at the moment. Not all are necessary and are being used. So this is part of the privilege spec, which is explaining what is the address of all these control status registers, what do they mean, how they are controlled. So the RISC-V instructions have 4 basic types. We identify register-to-register operations, operations that have constants in them. They are called immediates. And there are operations with 2 source registers, operations with large immediate constant value. Why am I telling you this? Just to show you for 32 bits how these different types are encoded. So this is how the ones and zeros that make up the instruction are encoded. On the left-hand side, you see the most significant bit. On the right-hand side, you see the 0. And these are the 4 types I was talking about. And you realize that the LSBs always contain the opcode, so that tells you which instruction we are running. This may be enhanced by a function because R-type, there could be several functions within the same opcode. And then you realize that the place where the registers are encoded are always at the same point. So this is the first source register, the second source register, and the destination register. And this is the reason why RISC-V chose them to be so at the same place, which makes hardware design for these things a little bit easier. The instructions are encoded into groups. So that was the first 7 bits we were looking at there. And at the bottom, you can see the matrix. What is interesting to note is that there are some parts of the encoding space is reserved for future use. But there is also something very interesting, the green parts. Some of the encoding space is free to use for custom implementations. And these will remain free. I mean, RISC-V has taken a description saying that no matter what, that custom 0 and custom 1 will be a free encoding space. Users are free to develop their own instructions and encode them within this encoding space. This gives you a very good opportunity to test and try out new instructions or enhance your specific instruction for that. Now, when you talk about RISC-V, it is a load store architecture. So all operations, that means that all operations are on internal registers. There are no operations that manipulate data in some memory address directly. What you need to do is you need a load instruction that copies from memory to registers. Then you have your other instructions, you add it, you shift it, you XOR it, or do whatever you want to operate on the values that you copied from memory into registers. And then you have store instructions to copy from the registers back to memory. In addition to that, you have flow control instructions. So you have to build loops, if else branches. So you need branch and jump instructions that round up your capabilities. Now, in a lot of these instructions, you need constants. And I'm talking now about 32-bit. It's the same for 64 and 128. The idea is to keep all the instructions with a similar length, but now you have a dilemma. You need 32-bit constants or immediates, but your entire instruction is only 32-bit long. So how can we do this? And the thing is that they realized in a 32-bit encoding, there are some holes which you can use to, fill in with a few bits of the constants, and then you can extend it to make one. I'm going to show you in a few seconds. There are also some instructions that help you to move constants and assemble constants together to form larger words. So we were talking about these different types. S and B are the same, actually. U and J are also the same. So these are actually 4 with 2 subtypes. And you see now, according to how the constants are encoded, these are the places where the constants go in there. Now, there is a downside of trying to make everything nice and regular. You realize that you optimize for the opcodes, functions, and the places of where you have the registers, and the rest of the space is filled up with those constants. And if you look at this line, for example, the assembly is very funny. So this is the first bit is here, the second bit is here, then come these bits, then come these bits. They all have their reasons why it is made that way. You make it easier for one part, you pay the price in some other parts. But this is where our constants are being hidden. So how does it work? How do these immediates work? So I'm just going to talk about 2 instructions to give you an example. It won't take long. This is now the load instruction. We are trying to load from the memory, and the way that we want to do is we need to somehow assemble an address. It's a 32-bit system in this case, and I need a 32-bit address. How do I come up with it? You realize I have a 12-bit constant encoded. I have the rest of the bits needed to say where I am copying my, where am I loading my data, and where is my address. So since it's not possible to fit the 32-bit address in the 32-bit encoding directly, what do I do? Just a second. Yeah. So I find out that, hey, I'm going to have a 32-bit value, an address stored in one of my registers. So this is the X22. On top of that, I'm going to add an offset. This is the immediate value, a constant, and I'm going to add them together to have my memory address. So this will give me a 32-bit memory address. These 12 bits will be sign extended, will be added to the contents of the source register to generate the memory address. Now, from this address, I'm going to make a memory access and I'm going to read the data, and the resulting value is going to be written into the register specified here. In this case, it's X9. This is the way it works. It seems to be overly complex when you look at the instruction. You say, why do I always have an immediate? I mean, why can I not only have the value here? So this is one of the things that they try to do with RISC-V. We try to minimize the number of instructions. And although this looks very complicated, you can do more with this instruction. So you have one more useful instruction that can be used in many different ways instead of having 5 different variants of the thing, all with slightly different parameters. So another trick that you use is in branching. So we have here one instruction. It says branch on not equal, BNE. It compares the contents of 2 registers, in this case, X10 and X11. And if they are not equal, we will jump to a location that is further ahead or behind. So now we have a similar problem. We need to jump to an address with the branch. And this branch is a memory address, but we cannot encode a 32-bit memory address in the same instruction. What do we do? So it's a similar trick that we use, but in this case, we have the program counter, which is pointing to the next address, and the jumps are then relative to this program counter. So what you do is you take the immediate, the constant, and we add it to the program counter. So we call this program counter relative addressing, and it works well if the addresses remain within some range, in this case, plus minus 4096. Is it possible to branch further? Yes, but we need then several instructions. We cannot do it in a single instruction. However, for most of those branches, they occur when you have a for loop, when you have an if else and things. That's when you have the branches. And let's say 99% of those branches are occurring within a short distance. So this type of encoding works very well with those. Now, the nice thing also about RISC-V is they were thinking about how shall we encode the instructions. And I was always showing instructions that were 32 bits. However, the RISC-V defines actually an encoding on the the least significant bits that tells you how long the instruction actually is. So if the least significant 2 bits are not 1, 1, then this is a 16-bit instruction. If they are 1, 1, the next 3 bits will tell you, will be 32-bit instructions, and so on and so forth. Technically, you can have instruction lengths with 16 increments from 16 all the way to 320, and even for 320 plus, you have an encoding that will allow you to define a wide variety of instruction lengths. Now, the good news is when we have a 32-bit architecture, we still have the option of defining instructions that are only 16-bit long. This is what we call compressed instructions. So if you have some common instructions that do not have so many parameters, there is a C extension, and it defines a number of instructions that fit into these 16 bits. And by using them, you can actually reduce the size of your code. Now, the trick here to remember is they are, it's not that if you're in a 32-bit architecture, once you have compressed instructions, you are executing twice as much. That's your microarchitecture. If you have a single issue system, every 16-bit instruction is still executed in one cycle. So what compressed instructions do in these cases is they increase your fetch bandwidth, because if you happen to have 2 compressed instructions, once you fetch 32 bits, you have your next two instructions. You do not need to fetch the next cycle immediately an instruction. And here you can see some of the publications from us where we have some benchmarks compared to different architectures. You see the differences between the green one and the yellow one. So this is RV64, G and GC. So G is a general Linux booting extension, which covers a few letters, and C is with compressed instructions. And average, you see a code size reduction by 34%, which is significant, especially if you are going to smaller embedded systems. So we talked about what RISC-V ISA is, but now I want to spend the rest of the time to talk about how we use this knowledge and how we build some cores. So the RISC-V ISA tells you the architecture. You know which instructions are supported, you know how they are encoded, you know what they are supposed to do. So it does not tell you any implementation details. It does not tell you, for example, how many pipeline stages you have to use, what memory hierarchy, what number and type of computation units you have, whether or not you are doing addition in one cycle or in 100, whether or not you are working in order or out of order. Everyone is actually free to figure out how to implement these. In the end, you have to be able to execute the string of instructions the same way as any other implementation. This is what the ISA tells you, not how you end up doing it. So you need to come up with a microarchitecture to implement it. Maybe your first idea is to determine which standard extensions you are going to support and how. And then according to what kind of performance requirements you have, you will choose your microarchitecture that best fits these requirements. Towards the end of the talk, I'm going to show you the different cores we have and how they fit. Now, when you talk about performance metrics, you have to also briefly understand what we are talking about. So here is a very rough description of them. So you sometimes talk about area. This is important because you pay on silicon per area. So the larger the core, the more expensive it is if you want. They're sometimes measured and displayed in what we call kilogate equivalents. That's essentially the number of simple two-input NAND gates. Or if the technology is known, you can talk about square millimeters, but you have to also know the scaling between different technologies. Just saying it is 3 square millimeters doesn't tell you much. Then the frequency or the speed of the circuit depends on the number of gates on the longest path of your microarchitecture. Power is more difficult of them all because it has two components. Leakage is dissipated even when you are not working. So that depends essentially on the area. And the dynamic power is dissipated when you are switching from 1 to 0 or 0 to 1 within your circuit. It is dependent on the frequency and the number of gates that are switching, so roughly also on the area. When you're talking about the CPU design, sometimes the more important thing you're talking is how many instructions can you execute per cycle. So if you have a single issue processor, the ideal would be you want to have 2 instructions executed every cycle. But sometimes you may need more time because some instructions are more complicated and you want to measure how efficient you are doing it. So this is technically measured in commonly used benchmarks. Benchmarks put common or is a way to put together a program, you run it, and by looking at how fast or how efficient it runs, you are implying, okay, this one is more efficient than the other one. For some smaller IoT devices or for larger systems where the power consumption is interesting, how many operations you perform per joule is also a very, very interesting point. So as a hardware designer, your job is to find a good balance between all these different things and to say, okay, I know what I'm trying to do and this is more important than the other one. The important thing to realize is one size will not fit all. So basically IoT applications and high performance computing applications have very different requirements, and the same architecture is most probably not, microarchitecture is not going to be efficient on both accounts. So this is also why and how we ended up developing a number of cores. Just going to give you a brief introduction to them. So we have what we call a low cost core, which is a simple thing that just runs your code. We have two variations of it. We will see in a few seconds. One uses the I, the other one uses the E extension, so 32 or 16 registers. Then we have our main workhorse. It's a DSP enhanced core. It's not only the standards, but we also have these extra extensions that add a number of instructions. I will talk about that in a few minutes. That enhance the standard RISC-V instructions. And recently we've been working on what we call a streaming core called Snitch, which we will not talk about today. And later on in the next hour, Luca is going to talk about more advanced processors, namely Ariane, which is a Linux-capable core in 64 bits. Now, the good news is we developed these cores, and as you can see, only the newest one is still under our development. The others have been taken away by organizations. So the low-cost core is now called IBEX by Low Risk. It's maintained by Low Risk. Open Hardware Group has taken away, the 32-bit main core and the 64-bit core. They named them CV32E40P. I'm not the biggest fan of their naming, and the Ariane is now CV6A. And this is great because this means that the cores actually mean something, they are usable, and other people in industry is taking over the maintenance of them and using them further in their projects. So let's give a brief introduction. So this is Zero Risky, or the name IBEX. This is as we had it. As I said, there are two configurations. They are the same architecture, both have two-stage pipelines. And we wanted to have a small core, as small as possible. So one is 19 kilogates, the other one is 12 kilogates. And the difference comes actually from these extensions. Zero Risky, the larger one, has 32 registers and has a hardware multiplier. And the Micro Risky tries to shed everything. So it uses 16 registers, and the multiplication instructions are emulated in software. This is why it can get even smaller. I told you, Low Risk has taken over this. So this is, they've put significant resources into making a better core from it. And you can also see they have a long they have plans, a roadmap, how to work on it. And you can already see this is where they took it over. So the core mark per megahertz, a measure of how efficient the core is, was at 243. And they are currently at 3. And they have further plans to enhance it. So this is all going all in well. Now, when we developed this first simple core, that was only for simple applications. It was for control, bookkeeping, but we are actually a research group. We are in energy efficient computations and doing things more efficiently, and we need more capable cores. So we will talk about that tomorrow. Mainly we use clusters for signal processing, machine learning applications. So we need something tuned for energy efficiency. I have a slide which will warn you towards that. That doesn't mean it's low power. It just means it does more per joules when you have it. And once we were looking into it, we realized, hey, the instructions are very nice, but we can do better for the type of applications. So there is the possibility to make extensions. We are calling them XPulp extensions to extend the capabilities. There are actually a number of them being developed. It's not only one extension. And we are obviously talking in the RISC-V working groups to make sure that these extensions are also ratified at some point so that we can, they can be contributed back to the community. So here's a very simplified pipeline just to explain what is happening. Basically, your program counter tells you where to fetch the next instruction that generates an address. You go to the portion of the memory that holds the instructions. You read the instruction. Notice that if you are supporting compressing instructions, you may need to align them, decompress them, and then you go to the decode stage. and you look at what the instruction is, you realize, ah, it is I type, R type, whatever. You realize you may have to read something from the registers. You forward them to your execution units. This is the heart of the processor, if you want. This is where the arithmetic logic unit is. This is that adds, subtracts, multiplies, and does everything. In parallel, there's an address generation unit for memory accesses, figures out where to write the data, and then you have the write back stage. Either your results are written back to the register file, or if you edit from the register file, once you have the data address, they are written back to the data memory. So this is a simplified pipeline for this thing, and this is how our 32-bit larger core works like. So it is a 4-stage pipeline. It's about twice as large, it is faster, and it includes all our extensions. To that, you can also add different options. For example, optionally, you can add a floating point unit, you can add privilege support and other things. And you see that the execution stage, depending on the type of operations you have, has ALU, MAC units, dot product units, or whatever extensions you have added to it. Now, I talk so much about custom instructions. Let me just say a few words. There is, as I showed, a reserved decoding space for custom instructions. So this allows anyone who's interested to add new instructions to the core. And the address decoding space is reserved. It will not be that in 5 years, RISC-V will need new instructions and will take that reserved space away. So that space will stay for custom user instructions. Now, the great thing is, if you have an implementation that supports custom instructions, like the core I showed before, they are still compatible with standard code. So if you have code compiled for a standard RISC-V processor, it will run without issues, because those instructions are in addition to the ones that RISC-V has defined. They will not interfere with each other, which is great. So in the worst case, you have your extensions. You don't have any way of using them, but you can just use a standard compiler that you can download from GCC and generate code, and it will still run on your thing. Now, if you want to take advantage of these additional instructions, the user has to provide some support so that you can take advantage of these instructions. This usually means you need to have a compiler that generates code for these custom instructions. Now, we regularly use these instructions in the 32-bit case. It's a great tool for exploring, figuring it out, what kind of changes can we make so that we are more efficient. And our goal is also to help ratify these extensions as standards through working groups. Think about it. If you can build a processor, add your own instructions, and then you can go back and tell the community, look, we have a great way of doing bit manipulation. We have implemented it. Without bit manipulation, we run it this fast. With bit manipulation, we have it. Here is a chip. Take a look at it, measurements, and you know, it's a much more easier way to discuss and to go forward than when it was not open and you didn't have this space. So for the RISC-V core, we have several additions. I'm not going to go into too much detail of them, just to give you an idea about what kind of things we are doing. So one of the things we added were post-incrementing load and store instructions. So you make the load and increment the value in the register automatically. Hardware loops, where you define a start and loop count that automatically does your loops. Several ALU instructions for bit manipulation, fused operations, immediate branch instructions. Very useful for our line of work are multiply, accumulate in different versions, and SIMD instructions, which say instead of using 132-bit operand, we can use 2 times 16 or 4 times 8-bit with scalar replication option, different types of comparisons. Let me give you an example. If you're using 8-bit values, the following, the one at the bottom, can be executed in a single cycle on RISC-V. So this is a packed vector dot product, and it takes 2 vectors of 4, multiplies them and sums them up all in one single instruction, which is great if you are working with 8-bit values. Here is now a brief highlight of what is happening here. We have a very simple arbitrary code. We are adding two vectors of a size 100. And if you were to compile this with baseline RISC-V, this is the code that you would get. It will take you 11 cycles to go through one of those additions. Now with auto increment load and store, you can actually save these additions in between. So you have 8 cycles per output. And then if you are able to set a hardware loop around it, now you are no longer having these branches at the end and the comparisons. You can directly go. That reduces it to 5 cycles per output. And now assuming that the values you're adding here are within 8 bits, you can use the SIMD extensions that reduces it further to 1.25 cycles per output, which is actually a great improvement just in terms of how many cycles are needed to, how fast does the program run, which is great. Now, I showed you 3 different 32-bit processors. So RISC-V, the blue one, is the one with all our extensions. There was the Zero RISC-V or IBEX, which has the 32-bit registers and the multiplier. And the black one is the one that has only 16 registers and has no multiplier. Now we are looking at different applications. In this case, we are using something that is used in an operating system. It's a scheduler. You're trying to schedule your tasks, wait for one to compete, and do something else. And here you see the number of cycles. It's normalized to the highest one. And you see essentially there is no difference in the runtime between these things. Because guess what? We don't really need a multiplier for these things. We don't need so many registers. And the instruction set extensions we have are not really shining for this kind of applications. Now, if you go one more step, you have to notice that the number of cycles is proportional to how long it takes to execute. So the less is better. And we are taking some embedded core, benchmark core, and you immediately see that the simple core is taking much longer than the more enhanced ones. The difference, the big difference here you see will come from the multiplier, because this multiplications inside this benchmark end up being done here in software. Here there is a hardware multiplier. There is still an advantage of using the extensions that we have added. You see that there is about 30% decrease in the speed, but that doesn't seem to be something for this type of application. But we develop these extensions for a specific reason. And a good example is now 2D convolutions. Now the change is much, much more significant. You see, compared to the simplest processor, you have 53 times better performance with the extensions, and even to the simple one, you have almost an order of magnitude in comparison. So the extensions are, they work. You have to understand for what kind of application you are working in. Now, the same thing obviously has a price. The core that had all these extensions is larger. So this is the size in kilogate equivalents. The smaller, the better from an area point of perspective. And all these extensions will have some additional, they will add to your area. And here you have the one with the 32-bit register file, and here you have the one with the 16. You have the 16 entry register file. And this is not little, because you see this is the area that is being occupied by the register file. It's I would say 1/3 of the total area of the core, and reducing it to half brings you down quite a bit. The other one that is missing is the multiplier. Here you have the multiplier extension. This is the multiply divide unit here, which is missing here. And if you look at it, that explains the difference between those two implementations. Now, this looks all very good and interesting, but what about the power? So we were talking about power. And once again, the power consumption in milliwatt at a certain technology, at a certain operating speed. The idea is to get better towards the bottom. Again, our 3 cores. And our more capable core, because it is bigger, because it is doing more, you will realize that it consumes also more power, and the smaller cores consume less. So this doesn't really look like these extensions are doing well. This is where you have to be careful, because energy efficiency is not the same as how much power you can consume at the same time, because energy is also related to the time. This processor is much faster. So here is an application scenario. We are doing 2D convolutions. It's from a more complex operation, but let me try to explain what is happening here. We have here the energy consumption on the y-axis. So the lower the better. And we are taking an image, we are doing a 2D convolution on it and computing something. And this happens every time we detect an event, we are doing this operation. The more, the x-axis shows us with what intervals we have these events. So if we are having a lot of events, meaning that there are, we need more frequent processing, we are on the left-hand side, and towards the right, we have less and less events. Now, the blue line is again the one, our extended processor, and it takes him 784 microseconds in this frequency to compute the 2D convolution. This is, notice that the scale here is logarithmic, so it is actually pretty fast. Now, the other core, remember, it was an order of magnitude slower, almost finishes the same task in 4.78 milliseconds. And because it takes so much longer, although the individual processor doesn't consume so much power, but you need to compute for 6-7 times longer, this means that the energy needed to compute this will also be more. Now look at your other core, the simplest core. Well, it takes 41 milliseconds, which is an eternity compared to this. And because it takes so long, also the energy consumption is quite high. Now, if you have fast events, if you need to run your convolution very frequently, it makes sense to use the extensions in this processor. But there comes a point, and this is a crossover point here, if your events happen every, let's say, roughly half a second, then this larger core is only used for a very little time, and all the rest of the time is standing idle. Then a slower core may be more efficient. And if you go even further, if your updates are happening every 30 seconds, now the black line stays below the other ones. Although it does the operation very slowly, because it's a small core, it will be more efficient when you go towards in an application where you don't need to compute so much. This is still not taking into account that you are shutting down processors. It's just, you know, the processors are running if they are idle and active kind of event. So there is more to be done, but it shows you what is going on in terms of energy efficiency, or why we have different cores, and how you can implement them. Notice that the same code will actually run on all of them. You have to be careful. This one has only 16 registers, so it's a compile time option, but it's essentially the same ISA, different options are being implemented. So I'm not so horrible with the time. So this was a short overview of the basics of RISC-V. I see that there is a number of open questions. I will try to go over them, and then we will have a break. I think we will still, we're a bit early. I don't know, Luca, maybe we start 10 past, which is probably better.
Sure. Actually, the questions are all answered but one. I'm answering them as they are typed.
Okay, so actually we can maybe take a little break and continue directly at 10. That saves everybody a little bit of time. So after the break, Luca will talk about more advanced cores. He talked only about the simple ones, and more discussion on performance, vector processing. And tomorrow we will learn about pulse systems, because cores alone cannot do much. They need a system around. We will talk about many core systems, managing data, acceleration. And then in the last hour, I will actually talk about integrated circuits from our group, what we learned, what are the specialties of these things. So let me try to see the questions and the ones that I can answer. Okay, I'm just trying to Oh, there are many questions. So let me first answer the simple things. The course recordings and the slides will be available. This is the first thing. Oh, let me see. So I think once we answer, they will be become available. Okay, I will answer some of them as Luca is presenting. Let me see. There is, for example, one question that is asking, let me take this answer live. Are the hardware loops implemented by software compiler or hardware actually realizes it? So the extensions that we talk about are in hardware. The compiler obviously has to map it to the capabilities of the hardware. So he has to understand what instructions have to be used to set up the hardware loops, but they are actually realized in hardware when we are having the expulp extensions. Yeah, so there is another question that I'm answering live. So the question is, with this custom instructions and this heterogeneous instruction set, how do you maintain a tool chain? How to maintain a compiler that depends on the specs of the extension of the processor? Because this all type of these sets makes very complicated the compiler. This is absolutely true. It is not very easy. So what you have to do is what we end up doing is for the instruction set extensions that we have to develop a patch. So you have to download the source of the compiler, then apply the patch, and make sure that your patch is not breaking and going ahead. So the ideal scenario for these extensions would be that at some point, the ones that are proven useful get ratified, make it in part of RISC-V, and then those extensions will be directly upstreamed into the GCC and bin tools and will be also supported throughout. So, and this actually is part of the ratification process. Now, will everything that we ever dreamed up be part of this thing? Well, probably not. Also, just as a side note, we are doing this for the 32-bit cores where we are doing mostly bare metal and smaller implementations. For our 64-bit cores, for example, currently we are not using any extensions for the same reason that you're pointing out. It's very difficult to maintain this type of infrastructure, continuously making sure that Linux boots, everything is recompiled. You're absolutely right. However, as a tool for research, for finding out if your idea, anything that comes into your mind, you say, why 32 registers? Let's say 48. You can try it out. You know, you can make your own extensions for that. Or AES instructions, does it make sense? So it allows you to build things without breaking everything around. So I think this is the great part. Let me see if, so there is one who's asking, how did you measure power spend in each unit of the core? This is a great question. It has, there are tricks. So we have a number of our chips, which we will talk about tomorrow in the second part, which have actually separate power supplies. But we also, once we manufacture a chip, measure its power, we also can run analysis tools on the same chip and have a one-to-one correspondence between the analysis that we make, which are not always so accurate, and the accurate measurements. Once you have the correspondence, once you know that, hey, my power post layout, power simulation, and my measurements match, or I know how they match, you can then have even very detailed minor units and do the analysis using software tools. But it's a combination of both measurement techniques, the way the chips are made, the way the power supplies are connected, and analysis tools and matching them together. Good, let me see which ones I'm a bit lost. I have to say done, so this was my problem, sorry. This we did, this we did. The ones that I'm not answering at the moment are the ones for which I don't. Yeah, so this thing is asked quite a lot. Is there a real-time extension plan for RISC-V, instruction for managing internal clocks, waiting, etc.? This is a very active research topic. So I would say 1/3 to half of our projects and discussions revolve around these things. You can be sure there will be a lot of work there, but the more industrial interest is in there, there is more discussions going on. So it's moving a bit slower, but there is a lot of work being done by many companies and many consortiums that is one of the burning questions. I'm not very sure if it is the answer you wanted to hear, but this is one of the major things that people are working on. The last one that I can pick is what support for security is offered through RISC-V Secure Boot. So this is part of there is a standing security committee, a task, not a task group, it has several tasks below it. And this is discussed through this task group. They are actually working actively on secure boot systems and extensions around it to do this. So it is part of the RISC-V Foundation work. Well, it is 10, so it is time for me to hand over to Luca, which is going to do the second part. I hope I'll be online answering questions as much as I can. And tomorrow we will continue with the chips. I think I have to stop Luca for you. Luca? Nice pair.
Yeah. You should see the screen now. Going to full screen. Okay, is the screen visible now?
Yes, yes.
Everything is okay? Great. I'll pick up my pointer. Cannot see. See how to pick up my pointer, maybe here. Okay, here. Okay, so we are ready to go. So welcome to the second part of the lecture, and today we are going to talk in this part about the design of more advanced RISC cores. So let's get going. So the structure of the lecture will be to look into the rationale for moving toward more advanced RISC cores, and mostly toward Linux-capable 64-bit RISC cores. Then we analyze the design and microarchitectural bottlenecks and look at some extensions toward supporting safety and security, and then also extension to support the vector operation. So, first of all, a bit of a context and motivation. This slide has already been shown. We have worked, and we are currently working a lot on developing 32-bit cores that are valid and very good and essential for the 32-bit domain, like IoT or microcontrollers and things like that. But you know, when you go to a more capable architecture system and the 64-bit of addressing space, and this is the space that is occupied by the 64-bit RISC cores. I have to say that in general, in the RISC-V community of development, hardware developments of the cores, the 32-bit space is much more populated than the 64-bit space. First of all, because the 64-bit cores, as we will see, are more complex from the design viewpoint. Second, because they are much more expensive to make in real silicon systems or expensive to instantiate on FPGAs. Nevertheless, there are several 64-bit cores, most notably on top, in addition to ours, for example, the Rocket and Boom cores developed by Berkeley, and their commercial versions that are available through C5. And there are also other implementations of 64-bit cores that are available in the open domain. The core we will talk about as an example and as a driver for understanding what is behind the scene in a 64-bit RISC-V core is Ariane, which is our open source core that has recently been moved to industrial maintenance, still remaining, of course, free and open source in the whole open hardware group. So that's what we are going to be talking about. So historically, we, there is a history of the evolution of the RISC-V that is usually based on myself saying to the team, I will never do something. And then after, a couple of years, we do that. So when we started the work on RISC-V implementation, I said, we'll never do a 64-bit core. It's too much effort. And then after 4 years, we decided to go for it. And so the driver for that, what convinced me that I was wrong, is that it's true that most IoT near sensor applications need 32-bit cores, but it is, and it's also not affordable to put a 64-bit of memory space in a small microcontroller, but fundamentally times are changing. So there are more and more large data sets, even in IoT applications, for which 32 bits start to be small. And there is the need to compute in some cases in big data analytics and several algorithms that require advanced floating point computation, even double precision floating point computation. And most importantly, I guess, also the very well-known open source source infrastructure is based on the Linux environment. So supporting properly Linux on large memory machines requires a 64-bit core with the capability of an application processor. So the capability of running a mature multitasking operating system, not a simple microkernel. And I would say last but not least, right now the race toward the high performance architecture is again open. There is not so much anymore a single vendor dominance. And so it's actually very interesting for the research viewpoint to see how to revive the research toward the high performance architectures. And so we do need 64-bit implementation in high performance computing. Now, the key research question and the reason why I was scared to enter into this room is it possible to still make an energy efficient implementation of 64-bit architecture? Is a picojoule per operation still feasible in 64-bit architectures, and how we can do that? So Ariane was our, and is our, create an open core to do research in these areas. It has the capabilities that are needed for the workloads that I was talking about in the previous slide. So it supports a virtual memory for a multi-program environment. So it supports efficient sharing and protection of the data in memory thanks to a mature virtual memory system. It has all the multi-mode support for an operating system. So, and we are aware of the fact that the operating system is a highly sequential code. So we need to design a core that is able to run highly sequential code at a reasonable level of performance. So a core that is operated at high frequency, because when you have sequential code, there is a very minimal instruction level parallelism that you can exploit. And so the only way around being fast is clock your processor fast. So operating frequencies that are in the range of a few hundred megahertz are not sufficient to run operating system sequential code in a satisfactory time. Then, of course, the idea is that you need to have a very complete, feature complete and robust core from the debugging viewpoint, because, and the functional verification viewpoint, because typically the workloads that you run are very large. Driver, application, multi-layer application software, firmware, and a lot of add-on libraries. So you need a highly verified and very mature, from the correctness viewpoint, implementation. From the hardware viewpoint, the fact that you have a larger address space, of course, makes your addressing and your data path larger. It becomes now a 64-bit data path for all the integer operations and the floating point operations and so on. And also it requires support for virtual memory. And as we will see, this is a major consideration in hardware complexity. It needs a support for MMU, which implies transaction Luca size buffers, TLBs, and page table walkers in hardware. It implies a support for multiple privilege level, and it supports for a more complex and standardized exception handling capabilities, as well as interrupt handling capabilities. So all this increase the hardware complexity and increase the support for complex software is what we targeted for our Ariane design. I have to clearly clarify that from the point of view of the performance, this is a very simple application level core. I would consider it more an application level controller. So it is not an ARM or even worse, not an Intel or AMD killer in terms of performance. It is a reasonable control core that can run a mature operating system. So as we said, it is an application class processor. And by application class mean it runs Linux and the Linux environment and Linux application environment. And it is Linux capable. So this implies for a standard Linux distribution, to be able to support a standard Linux distribution, implies multiple privilege level to support the operating system and the security levels needed for the multitask management. It supports virtual memory and also needs for sure caches. As we know, operating system and complex software infrastructure, traditional software infrastructure, not specialized for an application domain like digital signal processing, requires caches. So it requires an integrated, at least an integrated level 1 and cache for data and instructions, and also possibly a hardware page table walker for reducing the cost of virtualization in terms of hardware. In terms of target of this design, we targeted it's reasonable to target for this type of designs a frequency that is above 1 gigahertz for the reasons that I explained in the previous slide. Area, of course, is larger than what you would expect for a microcontroller, but since area is the premium and we didn't target a huge performance core, out of order superscalar core, our target area to keep cost under control is on the order of a few hundreds kilogauge. Nevertheless, this is several times larger than the small cores that Frank was talking about, 4 to 5 times larger, even 10 times larger if you compare with the smallest cores that we have. So it's a pretty large beast compared to the microcontroller cores, but it is still very small compared to a high-performance processor like ARM Neoverse or Intel i9 or something. It is also the high-frequency design target, 1 gigahertz plus, in a technology like 22 nanometer, requires a logic depth in your design that is not so big. So you have to be between 25 and 30, possible 40, if you use faster transistors, levels in your critical path. Which implies, from the point of view of the microarchitecture design, the choices you see on the right-hand side of this slide. So we needed to move from a flat pipeline that we use in microcontroller with 3 or 4 stages to a deeper pipeline, 6 stages, Why not deeper? Because if you make it deeper, then your complexity of a microarchitectural complexity gets very hard to manage. And also, targeting 1 gigahertz, a 6-stage pipeline is reasonable to is a reasonable frequency to achieve with the 6-stage pipeline. And we didn't add a lot of complexity, like out of order issue, multiple issues, and so on. But as we will see later, we needed to put the capability of having some sort of out of order management of the execution of the instructions to manage long latency instructions with a reasonable instruction set, with a reasonable instruction count, IPC. We also needed the branch prediction, because with a 6-stage pipeline without a branch prediction, your branches are already killing you. And this implies branch target buffer and a branch history table. So we went for a relatively simple architecture for a high performance processor. This is a super simple one, but very much more complex than a microcontroller. So to look more in details of what is necessary to build Linux on top of the basic things related to virtual memory, if you look into details of a Linux kernel, you start understanding you need more stuff. So this is where the complexity starts jumping up, and you start, not being so sure that you made a good choice to direct your research team into designing high performance processors. But so we needed, on top of the virtual memory stuff, if you start looking into it, we also need like atomic extensions. And also you need a multiple privilege level, at least a 3 privilege level, and a standard interrupt controller with core local interrupts, like timer and interprocessor interrupts. So we needed the extra. So as you can see, this is an example how when you choose to support in a given environment and a complete application environment, your core gets to jump up in complexity because of what is expected by this environment. And the porting of a reasonable software environment onto an application level core requires quite some work, and there is what you see on the right hand side is a non-exhaustive list of operations you just need to do to get your basic Linux boot. And this is quite a lot of work to be done, not to underestimate, for example, how you develop your bootloader and how you adapt existing bootloaders to your new microarchitecture. So let's look into the microarchitecture of Ariane, just to give you a feeling of how we went through successive stages to get this design done, and what is the complexity versus performance compromise that was chosen for this core. You see here the diagram with the 6 stages that I mentioned before. The stages are listed on the top of the figure. And now let's look, and you see fundamentally the microarchitectural block diagrams in the picture. So let's look at them in sequence of the life of an instruction, as you have probably seen in many of your computer architecture classes. So the first stage is dedicated to clearly the instruction fetch and and getting the data and getting the instructions ready from the memory system. So you have to generate your PC address, and your program counter, of course, can come from various sources depending on sequential or loops or branches. So then you go into your proper instruction fetch stage, what we call instruction set stage, and as you can see in the instruction fetch phase, you go through the virtualization support, and so you have your ITLB in the way to get your instructions. So after you have translated your virtual address into a physical address, you have to query your instruction cache, and then you get your instruction from your instruction cache in case of no misses. And you move into your instruction decode. Instruction decode for RISC-V is complicated by the fact that we support compressed instruction spec, which means that fundamentally the instructions are a mix of 16-bit instruction and 32-bit instruction. So there you need the realigner of the instruction stream. You need to do the decoding of the compressed instructions, which leads to an expansion of the compressed instructions, and then you have the decoder of the 32-bit instructions that leads to the decoded instruction. You also see that in this stage, we perform the proper decode after the realignment and the decompression. Then we enter, we go into the so-called backend of your execution pipeline using Hennessy Patterson traditional lingo. And in the backend, you have the issue. Here, we decided to go for a score-based, scoreboard-based design. Scoreboard, for people that are a bit rusty on this, is a simplified version of a reorder buffer. So essentially is a data structure in hardware where we store the instructions that are selected and put into the execution, and the intermediate states this instruction will have before being ready to be committed into the register file with the results. So the functional, through the scoreboard, we select the functional units that will have to be targeted by the instruction once the instruction is issued. And then we send the operands from the register file to the issue logic to be then used by the instruction units. Finally, we have the management of the instruction execution, which can be done out of order, thanks to the presence of the scoreboard that will manage the reordering of this instruction and the exceptions raised by these instructions. And this is done during the execution. And finally, we have the commit with the write back into register file. So nothing new, but you know, the design has to be made very solid, and debugging this type of non-blocking design is very hard. So in terms of maintaining the high frequency, this is a core that is not high frequency in the sense of what currently is achievable, that is around 3 gigahertz or even 4 or 5 gigahertz for highest performance processor in the most advanced technologies. For that, you will need even flatter pipelines and much deeper pipelines. Nevertheless, even with the 6 stages of pipeline, you need to handle data hazard, structural hazard, and control hazards in order to have a decent IPC. So just to recall you the forwarding issue when you have a dependency of an instruction from a successive instruction from the result of the previous instructions, and to manage the forwarding as well as long latency instructions as well as exceptions, we use the scoreboard. So the idea of the scoreboard is fundamentally a sort of reorder buffer where you store all the instructions that are in execution and their status, and you update the status, and you use this information to allow to have more than one instruction in execution over several functional units, and to track their status so that if there is an exception in one of the instructions that are under execution, the instructions that have been sent in execution after that in a speculative way can be squashed without damaging your state, your operational state. So this is fundamentally the role of the circular buffer implementation of our scoreboard unit. So if you have done your computer architecture class, this will look very much like a reorder buffer, where you have a data structure that stores the instruction in flight and manages 2 pointers, one for the instructions being inserted into the scoreboard, and the other for the instructions that are retired by the scoreboard when they have completed. So here, when you insert it upon issue your instruction in the scoreboard, and you see that you have several fields that qualify the instructions, the operand, and the status of the computation, if the result is ready or if there is an exception. So you see that here you can send several instructions in execution. Here we have, for example, 2 instructions. One is using the load store unit, the other is using the multiplier unit, and they're both in execution. And you can move along this direction as long as you have enough functional units that are available. So even though this is a single issue machine, so in each cycle a single is entered in the scoreboard, the extension to a dual issue machine is easy, relatively speaking, because of this capability of managing multiple instructions in the execution. So the logic connected to the operands available in the listed and tracked by the scoreboard allows to control the forwarding units. So, for example, here you see that from the ALU add in the first add and the second add, there is a need of a forwarding, and the information stored into the scoreboard allows to control the forwarding units when the results of the first ALU operation, the first add, becomes available and can be directly forwarded to the second ALU before going to the register file. So then you have your results being produced, and of course the results are stored into the result field. Why? Because we still have one long latency instruction, the load store unit, that is not yet ready to commit. When this instruction becomes ready to commit, we will commit. Unfortunately, this instruction causes an exception. Load and stores are known to cause exceptions, for example, TLB or page faults or violations of address boundaries because of security issues. And in that case, the scoreboard allows you to squash the execution of all the instructions that have been issued out of order without being yet committed. So, upon an exception, all the successively issued instructions that are not yet committed are cancelled, and the state is restored in proper sequential operations, so that the corresponding interrupt, the exception handler, can be run with the proper state. So this is fully implemented and open source in the Ariane implementation. And on top of that, of course, we also need the branch prediction. The branch predictor is one of the units, the execution unit here. And as expected, it performs the 2 main functions of branch prediction, which is a branch target buffer and branch outcome prediction with a simple predictor. And of course, this is an area where, thanks to an open source implementation, you can add and try your own predictors and your own strategies for branch prediction and see what is the effect of the IPC. Caches are also the other big crucial point to get right in a high performance processor. So in the Ariane processor, the caches, the level 1 caches, are tightly integrated with the processor itself, and this is essential for high performance because these are the low latency caches that have to feed directly the pipeline. So we went for a very simple and reasonable cache design. So 16 kilobyte, 32 entry, 16-byte cache line, and 4-way. This is also parametric, but parameterization doesn't come for free, in the sense that it will impact your cache, your cycle time if you want to make your cache much bigger. And also the data cache. As you can see, I would like to stress the fact that both are associative, with a moderate to high degree of associativity to help with the conflict miss rate. The L2 caches in this design is outside the core domain, and so it's not covered within the single microarchitecture. So one critical point that makes cache very hard to design in modern technology is that memory, SRAM, is comparatively slower and energy inefficient with respect to logic. So you need SRAM for your cache data because of capacity. You need enough storage density, so you need SRAMs, but you need to do something with the tags to make them faster. So at the microarchitectural level, we use virtually indexed and physically tagged data caches to achieve higher performance around the problem of slow memories. So just to recall that the fact that the critical path of the cache, if you're not careful, implies the in your critical path implies the tag lookup. Address translation, actually, if you do address translation, you have the problem that your address translation gets into the critical path because you perform virtual to physical address translation before doing the lookup in your cache. So we decided to go for virtually indexed and physically tagged cache for the reason that with the virtual index, we can perform the access in the cache memory, which is the slowest one, before the address translation. And physically tagged, we have faster cache, we have faster tag because they are smaller. And so we can do the translation before checking the tags. So we can have the tag check performed already in the physical space while we do the access of the data in the cache in parallel on the part of the virtual index. So this allows for a faster implementation and also allows to, in the physical implementation, the skew the access time to the caches, to the cache banks that are the slowest one. So the memory management unit is very critical because it's in the way, as we have seen, for the critical path as well. And it has to support the multi-level virtual to physical address translation. So in RISC-V, we have several levels. So in Ariane, we support 3 levels of cache of page tables, as shown in the slide. And we also designed the hardware page table walker to allow to efficient TLB mismanagement. Without going too much into the details, the working of the hardware page table is fundamentally aimed at automatically walking the page table, following the links, the pointers into the page table to get to your final virtual address when you have a page miss. So in case of page miss, the hardware page table walker that is designed in Ariane allows to walk multi-level page table automatically, accessing the page table entries until you get to the leaf of the tree where you finally have your page table, virtual page table address that you will use to store in the TLB afterwards. The microarchitecture description, as you have seen, this is nothing fantastic, but the overall implementation and debug of this complex logic is something to be taken into account very carefully. So one very important point that comes with designing an application level processor is to be able to provide to programmers, both in the debug phase, but also most importantly in the application level development phase and optimization, interfaces, standard interface to debug and trace. So the standard debug bridge that is supported for Ariane, as well as a number of performance counters that are useful in optimizing applications, such as tracking the number of cache misses and issue rates and things like that. This part of the tracing specification of RISC-V is actually a working group in the RISC-V specification groups, and it is and we actively participate to this group to define a standard set of trace commands and trace status that can be used across various implementation of RISC-V processors. So verification, I hinted several times that the verification of an application level processor with integrated cache in a complex application system is a major challenge. So this is where actually we learned a lot in verification, and so the type of verification that is performed to get these processors in a working state, capable to boot Linux and run important complex application, is that you have to start from basic unit tests that are testing your capability of run programs, simple programs, and there is a quite interesting set of tests that you can assemble, run. These are called the RISC-V tests to verify the basic functionality, but this is usually not sufficient to really test even the single processor in its isolation. So you need more advanced testing and verification methodologies, such as, for example, constrained random verification, which fundamentally means you generate random programs that you will never have considered to produce, and then you run these programs and you compare the execution of these small random programs against a golden model, which is an instruction simulator, for example. And then you figure all the differences and check for potential mistakes. This is leads to a higher level of verification on top of directed program tests. That is the first level. There is actually a very interesting open verification framework based on UVM provided by Google, and the number of this type of verification frameworks provided openly in the open source domain by various vendors as well as companies increasing. And this is actually one of the big benefits for having this course industrially supported, because you can get professional verification done on the course. Then the two next level of verifications are very important after you have some trust into your unit level verification, is to integrate your system into a working system on chip, for example, implemented on an FPGA, which implies having also peripherals and access to the memory system, and then to run continuous integration. Continuous integration is fundamentally a very large set of application and benchmarks that you run all the time and continuously every night, every time you touch the core. And this actually helps increasing and finding new bugs in the course, and has to be established and run. So I just mentioned that in order to provide a reasonable verification environment for the last step of the validation of your processor, you needed to have an SoC type of environment. So the unit test is not sufficient, and then to do something with the processor, both in verification and application, you need a system on chip. In a Linux-based system on chip, this is not so trivial, because it has quite a lot of requirements. You need, at least as shown in this picture, on top of your core, that is here, you need at least a system interconnect. And in this case, we use the standard AXI4 interconnect-based system. And then you need interrupt controllers, UART. You need access to the main memory through a memory controller. You need access to boot ROMs, and of course access to JTAG and all the debug features. This can be relatively easily implemented on an FPGA, which provides you already, for example, the physical memory controller that you need in order to access DRAM, and then you have to provide, if you want to support the open source core, you have to provide a FPGA bitstream so that people can download the bitstream and get working on your emulated SoC to get their application ported on FPGA and tested and debugged. So this is what is provided with Ariane on top of the core that you see here. Now, this is a super simple system, as you can see, because it's a single core, and you know, basic memory and basic peripheral set. What if you say, well, my research is on many core architecture, advanced cache coherent architecture? So you also have, thanks to open source collaborations across the ocean, in this case, with Princeton, and here you have the integration with OpenPython. OpenPython is a research infrastructure for scalable multi-core and many-core accelerators, and Ariane is actually included in OpenPython, embedded in OpenPython, as you can see from this slide, with a cache-coherent interface. So in this case, the baseline Ariane that was described in the previous part of the talk is integrated with a cache-coherent block that manages the interaction with the level 1 cache that is embedded in the processor itself, and has an intermediate level of cache called 1.5 cache in OpenPython that provides the final interface, the cache-coherent distributed memory system, where you have, for example, distributed L2 and then access to a network on chip for multi-core cache-coherent network on chip-based systems. This is available also in terms of bit stream for large FPGAs, and it is able to boot SMP Linux. So I just want to stress that this is quite a major achievement, because this is fundamentally a fully open source multi-core, many-core system, all completely available at the RTL level, and for which you could even consider making a chip if you have enough money to pay the area of such a large chip. Now, still talking about the advantages of open source, which is in a sense an orthogonal team, but with RISC-V and RISC-V open source implementations like we do, it's always interweaved with what we do. You see here that the open sourcing of Ariane in 2018 actually has been instrumental to creating a complete ecosystem like what I showed before, where we integrated together with other groups Ariane in many execution environments, and the OpenPython one is only one among the many. And also we are looking into integration and support for standard open source tools, not only commercial tools. And for example, Ariane is available with a Verilator, is supporting Verilator simulation. So you don't even need a proprietary and commercial simulator to run the RTL on Ariane. And you know, the integration of Ariane and the support of Ariane by a group of companies, the Open Hardware Group, is now making it easier to integrate Ariane, for example, in modern verification environments that are made by open source components that are maintained by various companies. So, for example, this plot shows how you can integrate Ariane as a device under test, shown here, into a complex verification environment that uses, as you can see on the bottom, a commercial golden reference by Imperas and UVM reference model of the core for the verification, uses a Google-based random instruction generator for random test-based verification of the core, and also the possibility to integrate various types of memory models, cache hierarchy, and so on with the inner core, and have a complete verification environment that could be run on Amazon Cloud. Now, enough about the higher level. Let's now go into the hard silicon implementation. So Ariane has been typed out and demonstrated in silicon multiple times. The idea of doing in silicon is also very instructive to really understand what is the cost in terms of hardware, performance, area, power, energy for your silicon, for your advanced features needed for booting Linux. So is booting Linux cheap or it is expensive as a feature that you would like to have for your core? It turns out it is very expensive. So let's look at the silicon result. So this is an implementation of Ariane in FDX22 technology. So the basic features of Ariane are summarized here, as you remember from the microarchitectural discussion we have. And here you see that the target for the implementation in silicon are actually achieved. So the design was closed in worst case at around 1 gigahertz, and actually in nominal conditions, it's working faster than 1 gigahertz. So it is meeting the target. The core area is, as expected, larger than 100 kilogates, is around 175,000 kilogates. And if you put an advanced floating point unit, it reaches the 200,000. Now, the message I want to give you this slide, which I think is a very interesting insight, if you have, if you're working in the architectural space and you want to go, you get your hands dirty into real hardware design, you see that even relatively simple support for advanced application features is very expensive. Just to mention two elements that I described in my microarchitectural description, and not at random, the TLB implementation and the page table walker and the scoreboard. This relatively simple features take half of the area. And the reason is that this is memory. Memory is large and slow. And to make it faster, you have to use very large memory, not so dense memories, or even flip-flops to implement your memories, or latches to implement your memories. And so you see that a lot of area, and by consequence, a lot of power, leakage power as well as dynamic power, goes into these data structures and control logic needed to support your application execution. And in fact, if you take a numerical view in terms of your energy, you see that the cost for running on an application processor a stream of RISC-V instruction goes from at nominal condition, which is 8.8 volt in the same technology, which is the 22 FDX technology, there is a factor of 5 abundant cost in terms of energy per instruction. So same technology, energy per instruction from a microcontroller level core to a application level core, the cost in terms of energy goes up by a factor of 5 to run sequential code. And remember, this is not speed, this is energy. So it's power multiplied by time. So this processor is faster because this in this technology, a microcontroller runs roughly half of the frequency, so 500 megahertz. So here we are running at 1 gigahertz. So speed is double, but the cost in terms of power is much higher. So that we have even factor of 5 worse energy per operation. So it is not for free. So the why we have all this increase in energy, the explanation, the simplest and clear explanation is over here. Larger data, of course, that we manipulate, but a larger data path, but most importantly, a lot more area dedicated to stuff that in an application level processor you must have, in a microcontroller you don't need. Now, we can wonder how we can recover some energy efficiency here. And the next last part of my talk will be exactly on that. How we can make this type of application level work more efficient from the point of view of the energy efficiency. So one, of course, is that you don't always need to work on double precision floating point numbers as or on 64-bit numbers. And I'm taking here the floating point case because this plot shows how over time a very important floating point application, probably the most important today floating point application, that is machine learning training, has moved from full double precision floating point to lower and lower precision, thanks to algorithmic improvements and a lot of work done to better understand the algorithms that you do in machine learning, and this actually led to viable implementations over the years of training of machine learning algorithm in training that are, 16-bit, or even some people are talking today about 8-bit. Of course, you need a floating point in training because of dynamic range, but you can see that you have quite a degree of freedom. So what we integrated in Ariane and recently released open source also independently, it's called Trans-Precision Floating Point Unit. And this is actually a floating point unit that you can use to run either 64-bit floating point calculations or 32-bit floating point calculation in SIMD mode, SIMD2 mode, or 16-bit floating point computation, either a normal standard floating point or extended range floating point, also called brain float, and finally even 8-bit floating point with the SIMD8 capability, whilst we have SIMD4 for 16-bit. So this is clearly an advantage, because with a single operation, you can single instruction, you can get, in this case, up to 8 FMAs in a single cycle. This, of course, if you play with this, you bring your energy per operation down very significantly, since you are getting with a single instruction many more operations done on a smaller bit. So using SIMD mode, trans-precision, and tuning the precision is a way to get more useful work done in a single instruction, and so get your instruction, your operation energy lower, thanks to lower bit width and SIMD mode. This is actually confirmed by silicon measurement, and it shows that actually by moving from 64-bit operations to 32-bit, then to 16, and then to 8, you have a superlinear improvement in energy efficiency of the operations. The reason why this improvement is superlinear is that not only you perform 2 operations in the same cycle because of your SIMD mode of operation, but also because you can run your smaller floating point units, 32-bit and 8-bit and so on, in a smaller number of clock stages, because you need to pipeline the floating point operation less, since the operands are smaller, and also fundamentally because the arithmetic logic needed for fuse, multiply, accumulate in floating point is a quadratic logic. So if you go with a larger floating point unit, your cost in terms of number of gates increases superlinearly. So you have a joint energy advantage due to the fact that you run in a shorter number of clock cycles. So remember, energy is power multiplied by time. And also the fact that you run SIMD, and finally the fact that you have a much superlinearly simpler. So again, SIMD is a very good idea to recover your energy efficiency, especially if you work with floating point numbers. But actually, this is not enough. What if you want to not only get more work done with a single operation, but also amortize in a better way the cost of all this application luggage that you have? So the cost of the TLD, the cost of the page table walker, and so on. How can we get then more real execution units into the area, so that the ratio between execution units and logic, control logic, and storage, caches, and so on goes up a bit in favor of the execution units? Well, the idea is to couple your high performance control processor with a data-centric engine, which fortunately we have in RISC-V a standard way to do it, which is supporting the RISC-V vector instruction set. So the idea is to couple your control scalar unit that performs all the stuff you need for application level running, so virtual memory and privilege execution and so on, with a vector engine that you are going to use with a vector instruction set to really do the number crunching. Now, the vector engine is a different beast because it can be designed with execution throughput in mind. Doesn't need to worry about all the complex things that are in the application environment which you manage with Ariane. So we developed the complex, which is made by the Ariane core and the ARA core, which is a vector unit. The vector unit, as a refresher from your computer architecture classes, a vector unit is an array of capable floating point unit. Here I put floating point, double precision floating point, but precision floating point, so they can also support the smaller bit width, with a very large register file, which we call a register file, vector register file, multi-banked, that will feed the operands to the lanes of your design. And of course, you need memory access to get from your caches the data needed to feed your register file and your units. So you need a load store unit to interact with the vector register file. So remember that when you design a vector unit, now your hunger for data coming from the main memory is much bigger than the hunger from data that you have with the scalar unit. So you always have to worry about your roof line, and the roof line has to be tuned in a way that for the computing intensity of the kernels that you target, you get a reasonable utilization of your floating point unit, which basically means being in this area of the roof line. If your target computations are in this area of a roof line, you are okay, because you are fully utilizing your floating point units. If you are in this area, it means that you are bottlenecking on the memory link and you are waiting for the cache all the time. So ARA is designed in a modular way so that you can separately decide how big you make your bus in the cache and how many lanes you use. In this case, by modulating these two values, you will change the corner of your roof line. Here, you will move it back and forth, and you will move your roof line up and down. The height of the roof line is the number of lanes, and the corner here is determined by how wide you make the bus in the cache. So, for a design that I'm going to talk about today is for a 4-lane unit, and the ARA target is 0.5 double precision floating point operation per bit, so around here. And you can see the bottom, corner of the roof line is here. Okay. So what is a vector floating point unit? The idea is that you want to amortize the instruction fetch stuff, that is the one that is expensive because it needs the TLB and all the translation and all the fetch cost and so on. And then you want to have a vector instruction that executes for a very long time. So the idea is fundamentally to be able to develop lanes of execution that contain your floating point unit, and these lanes of execution will fetch operands from your register file. This is a very large register file, and again, the memory, the memory problem comes about once more, because the register file is big and has to be made by memories. So you have to be careful in accessing this register file, because a register file access is very expensive. In order to make the maximum bandwidth out of the register file, we put operand queues made of flip-flops in front of the floating point units and at the exit of the floating point unit, so that we can manage the access in the register file in a more efficient way, without needing a fully multi-ported register file that would be very expensive to implement. So these are the reasons why we have these operand queues in front of the units and at the end of the unit. Then the floating point unit will execute independently in the various lanes, and of course the operations will have a different latency, and we use the output queues to be able to have non-blocking operation of the non-blocking pipeline operations of the unit. Then we have the interconnect that is part, if you want, of the register file, which links the operand queues with the register file banks. And so this is a critical design point, because you need to be able to feed operands to all the instruction, all the operand queues in front of the lanes. And this is actually a very large register file made by fast memories. The operand queues are already described. And then fundamentally you design your system from the physical implementation backend in lanes. So each lanes contain the data path that I described before, a slice of the register file, and a slice of the interconnect. And then you have externally to the lanes, you have a load store unit that will have to get the data out of the memory system and distribute it into the register file so that it can be then ingested by the lanes. And then you also need an instruction sequencer coming from the master processor Ariane to decide what you have to do, if the operations or the load and store. So this is the Ariane interface. Okay, so it's clear that you have to be very careful with the load store unit, a single load store unit, because the load store unit has to distribute operands to all the register file lanes that are in the lanes, operand lanes here. So this is a one-to-many distribution of operands. It can be quite expensive. And so you have to be very careful about your design of a vector load and store unit. If you want to make a very large vector unit, you may need more than one vector load and store unit. We will see how much we pushed this single load and store unit design in ARA in the next few slides. Okay, so after you design a vector processor, you also have to be very careful in using the vector processor in an effective way. So, for example, how you perform matrix multiplication on this vector processor. Matrix multiplication is a very important kernel and also shows a bit the capability of your vector unit. So here the idea fundamentally is that try to implement your matrix multiplication in a vector-friendly way. And the idea is to use, some sort of a set of reductions, so a set of accumulation variables for accumulating the partial sum of your column by column products. So, as shown here, this is your first row of the matrix, and you will compute the result by accumulating the partial results of the various columns that are multiplied by the elements of the row. So this is the way we are going to do it. So we are going to have fundamentally use the floating point units, floating point multiply accumulate units in the lanes to accumulate the partial products of the row by column that we are computing in parallel with our vector lanes. So you take the first operand and you multiply it for the first columns, first 4 columns in parallel, using the 4 parallel multiply accumulate. So you distribute this operand to the 4 lanes, and then you do second operands and you accumulate, third operand and you accumulate, and so on. So in this way, you use very effectively your FMAs, and you can achieve a very high utilization of your vector lanes. So here you have the code. I'm running out of time, so I don't want to spend more time on the code. You can look it up, and then this is actually showing how your vector units are highly utilized over time. And the only underutilized part of the vector units during the matrix multiply is for the load of the operand that of the first matrix that you get as a scalar from the Ariane processor. So this is also suffering a bit in terms of utilization because the Ariane processor is, and the interface of the Ariane processor with the vector processor is, blocking. And so when you are fetching the operand from the scalar operand that from the first matrix from Ariane, you are idling the floating point units in the vector processor. Nevertheless, since you are making such a good use of the units, you don't have such a big underutilization. Results are shown here, and as you can see, for matrix multiply, the processor, the ARA processor, as long as you go, as soon as you go toward fairly modest matrix sizes, this is 32-bit, 32 elements, 64-bit, and so on, you are really at just a few % from your roof line. In this region, actually, you are limited by the issue rate of Ariane and not by the memory bandwidth that you have in the memory system of the vector processor. This is actually an artifact of the fact that Ariane and the interface between Ariane and ARA is very simple and blocking. So, an area for future improvement. Okay, let me just move to the last part of, again, after the microarchitecture, we go into the physical. And this is the physical implementation of ARA. As you can see, it looks even without a need of a pie chart, you start seeing that this is better than Ariane in terms of utilization. Why? Because all these lanes are execution units. So instead of having only fairly small percentage of area dedicated to an execution unit, a single execution unit you will see in Ariane inside here, you have a fairly large area dedicated to execution units. So it means that if we can keep this execution unit busy with a high utilization, we'll get a good performance of efficiency out of our silicon, because our silicon will do most of the time floating point operations, which is what we care about, and use 80% of the area to do floating point operation. Again, it means that we are using our silicon efficiently. So, in terms of implementation, the clock speed of Ariane and ARA can be matched. So actually, ARA is slightly faster than Ariane, but just a minor difference. The area is fairly big, but this is not a big problem because it's big because double precision floating point multiply accumulate are big. So you are doing big operations. And so as long as you keep this unit busy, you will be very efficient. And in fact, the efficiency gap, remember, it was a factor of 5 with respect to microcontrollers. Now we can achieve 2.5, between 2.5 and 3 better than Ariane in terms of efficiency, which basically means that we are now still in a high performance environment, but we are just a couple of X away from a microcontroller environment. So we have been able, with a vector processor, to reduce the energy efficiency gap by a significant amount. If I scale this larger, to the largest instance that I can manage to manage with this, to instantiate with this architecture with ARA, which is a 16-lane instance shown here, which is actually a fairly big chip. This would be something that competes with the Fugaku chip in the top 1 supercomputer in the world. Actually, 16 ARAs will give you, in a single chip, 16 of these guys, of 16-way ARAs, will give you 1 teraflop in 12 watts. Actually, not bad at all. And it would, compete with the top-of-the-line vector processors. So, the idea of using a RISC-V in high-performance computer, which is my last slide, is actually a very interesting idea. It was, considered crazy a few years ago, but now it's not, especially after we have some silicon and quite the evidence that demonstrates that you can design a high-performance architecture with RISC-V instruction set, vector instruction set, or other tricks that we'll see in the next slides tomorrow. So the RISC-V processor is actually an integral part of the EPI, European Processor Initiative, that has the target to develop European technology for the next generation high-performance machines that is, in a sense, so independent from IPs that is not owned in Europe. And so this is actually a very strong and big challenge, because it will go on for the next few years. And the idea is we will be able to design competitive high-performance architecture using RISC-V IPs. I believe we will, but you know, it's a long story. So I'm done with my lecture for today. Thank you. And I've seen many questions. I'm sure that Frank has answered to many of them, but I'm open to further questions now.
It was a strong typing session for me.
Okay, so I see I see a couple of questions that are open now. So what is the target of a formal verification? So, well, primarily the target of a formal verification is matching the implementation, RTL implementation typically, with a golden model that has been specified in a formal language. So you have a golden model specified in a formal language, which is fundamentally a logic language that specifies the implementation and the functionality, and then you automatically, using various techniques that I'm not going to, of course, cover today, you will verify the matching between the golden model and the implementation. There are also other forms of formal verification, such as verifying properties. For example, never deadlock on the memory. And this is also typically based on assertions. So you specify with the logic language as something that your design should always do or never do. And then you run the formal verification to verify that these properties are actually, these assertions are actually verified. Yeah, so is there any other question? No open questions, actually. Good. So I think Frank was too efficient in answering the questions, so I'm happy to see that. And no further questions, so we can you know, stop the lecture, have some well-deserved rest.
Oh, there are questions when you say.
Okay, yeah, you know, there are many people in the audience, so I expect many questions. So, is it worth to work to speed up the OS? Okay, that's actually a very interesting question. You know, in many cases, your application can afford very long sequences of instructions that are you know, application sequences, so it's the OS per se is not a bottleneck. However, in many workloads this is not the case. Especially, you know, if you are not in a supercomputing environment, you have many cases where you are time multiplexing. You have a lot of small tasks that you need to handle, and in that case the operating system always gets in the way, and so it also is very important for handling security, handling exceptions, and so on. So my impression that is, even if you're not in a super careful optimized application environment, you know, making sure that your application, your operating system is efficiently executed is very important. And it will contribute significantly into performance. So in application environments that are not very well controlled, which are, for example, mobile phones or you know, edge servers and things like that, then your OS is super important. Is Ariane detailed specification publicly available? Yes, Ariane is documented, and the specification of Ariane is available. It's on GitHub. There are lots of documents. And I guess what is missing a bit from Ariane is really super detailed tutorials. So the documentation are pretty terse, and so they are really more like working documents. And the type of tutorials that you can expect in Ariane are at the level that we have been doing so far today. I expect this situation to improve significantly, since now Ariane is being taken over and maintained by industry. Will be a large industrial project and products based on Ariane, so there will be a lot of documentation coming up with these projects and products. Do you think RISC-V processor will use in future supercomputers? Well, you know, I don't think, I'm sure, because we are going to design them. No, but joke. You know, it's going to be a difficult ride. It will need major investments. But you know, let me just take an example: Fugaku supercomputer, which is you know, according to the current top 500, is the top supercomputer by a fair amount. It is based on ARM vector processor, RISC-V, and actually it is a new design done by Fujitsu, and the RISC-V specification is not even 5 years old. So it means that you can design with enough capabilities, enough investment, from a specification of an ISA to a leading edge supercomputer that wins the race over all the computers in the world in terms of performance in you know, 5, 6, maybe 7 years. So why not RISC-V? If you put enough money into it, there is nothing that prevents RISC-V to win the race in 4 to 5 years. Is there a standard RISC-V extension from precision floating point unit? No. This is a typical case where they went ahead with a non-standard exception. We are seeing an extension. We are seeing a lot of traction around this trans-precision floating point unit, and I expect that what will happen is similar to what happens with our XPulp instructions, that are becoming a proposal within a standard specification group. It is for the XPulp instruction described by Frank in the previous part of the lecture. This become a part of the DSP standardization group and are gradually being transformed in a standard. Maybe modified because other people would you know, have good suggestion, improvement, they contribute to the group, but the idea is that they will move into standard and they will be ratified relatively. For what concerns trans-precision, I expect the path to be the same. And the reason why I expect the path to be the same is that right now, anybody that does machine learning knows that you cannot only do with floating point. You need the 16-bit floating point, and most of the times also 8-bit floating point type of format. So the RISC-V community is clearly realizing this, and the standardization of the sub-precision floating point will actually be for sure happening the next few years. Okay. Yeah, there is actually a very good link here in the dialogue, that there is a repository of RISC-V resources, including many open source implementation, including ours, because I remember providing information to this awesome RISC-V site, and I think this is actually very useful to have this type of curated resource lists, so that people can look what they can find in terms of open resources available. So there is RV64 always treating 32-bit integers assigned as mistake. Okay, so I'm not sure about this. This is a bit detailed. Don't know how to answer to this. Sorry. Which is for you the next step for reducing the performance gap of RISC-V in comparison with other chips, ARM, AMD, Intel? Okay, so that's an excellent question. So I think that there are two directions. One is the direction that is being taken and will be taken more and more by industry, because it's a very engineering intensive direction, which will be to go through the various paths of evolution that will make RISC-V implementation from simple application level, like I showed this today in terms of Ariane, to superscalar, out of order superscalar, and so on. So this path is a path that there are many people that know how to do, because it has been done many times for many instruction sets. And if there is a market value for that, it will be done. So for example, Sci-Fi is right now announcing higher performance processors. There is also Western Digital that is announcing higher performance processor. In China, Baidu has been announcing a pretty good performance processor. So far, we are not yet talking about the performance level of AMD, Intel, or ARM, but the gap is closing. So that's one direction. I would say that this direction to make a high performance superscalar out of order processor is not something super interesting for universities. University can do maybe components of this, but it's a lot of engineering. The other way to close the gap is to actually be creative in terms of using your instruction set in new ways. So for example, how to create the next generation of highly parallel execution engines that are not a superscalar processor, or not a GPU, but are something else. And this is actually what we are trying to do. And I think other groups are also trying to do. But if you want to see a bit of a glimpse of that, look at our hot chips paper that is coming out this Manticore, and basically shows how you can beat GPUs on their own terrain in terms of efficiency, using a high performance, highly data parallel architecture based on RISC-V. The big and nice thing that makes me super excited about RISC-V is you can really play with the instruction set architecture and the microarchitecture. There are no boundaries that you cannot violate or explore. So this is actually what makes, in my view, and then you can push this exploration at the architectural level, at the ISA level, into silicon, into implementation. And this has never been possible in research in the past, unless you were, committing to a proprietary instruction set. So what RISC-V has done is exactly this, and this is fantastic. And so I do think that it will help. We will have leading edge efficiency RISC-V based architecture next 3-4 years.
Yeah, Luca, there is, I think, one more. It ended up in the chat. It's asking the custom binary 16 alt is bfloat 16 format. And this is actually true. We started calling it binary 16 before bfloat came out. So they actually ended up being the same thing. I think this is it for today.
Thank you. I hope it was useful. Between today, we also upload a document with the references, so you can read up if you want to know more, and we'll see you tomorrow.
Yeah, hopefully we will see if you liked it, because if tomorrow there are less people, we know that they didn't like it. Okay, bye-bye, everybody.
Bye.